We present blurred LiDAR for sharper 3D, robust handheld 3D scanning with diffuse LiDAR and RGB. LiDAR is widely used with RGB images for 3D reconstruction and scanning. RGB-based techniques, such as neural radiance fields, have become widely used for 3D scanning in applications like handheld, robotics, and VR. Yet, these RGB-based methods struggle in challenging low lighting, low texture, and low albedo scenes. In these cases, LiDAR can help provide depth cues where RGB images may fail. The conventional LiDAR casts a sparse grid of dots onto the scene and records timing returns for each dot, which correspond to precise depth values. These values can then be easily used to supervise any 3D reconstruction technique. However, these conventional sparse LiDARs might struggle when there's limited input views to your 3D reconstruction. For example, LiDAR might be providing the primary depth cues in this scene's low light, low texture, and low albedo regions. However, because the sparse grid of projected dots doesn't sufficiently cover the scene on limited input views, the resulting 3D reconstruction has poor geometry estimated in these low texture and low light regions. In this work, we propose using RGB with an alternative diffuse LiDAR for robust 3D reconstruction in these challenging low texture, low light, and low albedo scenes. Counterintuitively, we find that this diffuse LiDAR, which records blurred measurements of depth, can actually improve reconstruction in these challenging settings. We first provide some background on these sensors and consider a widely available diffuse LiDAR which is commonly used for proximity sensing and retails for about $10. This LiDAR emits a diffuse flash over the scene and records low-resolution 8x8 pixel timing returns, where each of these pixels captures a wide instantaneous field of view of the scene. In other words, each LiDAR pixel records time-encoded depth measurements for a wide portion of the scene, resulting in blurred or mixed timing measurements. Our first key insight is that these diffuse LiDARs can improve the spatial coverage over sparse LiDARs, especially when considering a limited number of input views. Because sparse LiDARs emit a sparse grid of dots onto the scene, they have very precise depth resolution, but they have very poor spatial coverage. On the other hand, our diffuse LiDARs have much better spatial coverage, but also introduce an ambiguity into these depth measurements. However, just because we have blurred or mixed returns doesn't mean that the information about depth is completely lost. We can actually use the timing returns of photons, otherwise known as transients, which encode the spatially mixed signal over time. We can model these spatially mixed time returns in our analysis by synthesis approach to deconvolve these different depth measurements in our reconstruction. Now, this diffuse LiDAR still has a low 8x8 pixel resolution. However, our second key insight is that the spatial ambiguity of the diffuse LiDAR can be resolved using RGB images. RGB images provide dense spatial and color signal, but might struggle in these challenging low lighting, low texture, low albedo scenes. Diffuse LiDAR, on the other hand, provides coarse but robust signal under these challenging scenarios. We propose using the complementary strengths of these two sensors in our analysis by synthesis approach. We leverage the signal from both of our sensors, an RGB camera and a diffuse LiDAR, in an analysis by synthesis reconstruction. We start with inputs from both of the sensors. First, histograms, which are discretized versions of the transients recorded by the diffuse LiDAR, and the standard RGB images. We then render or synthesize these measurements using a Gaussian surfel-based representation. We use this Gaussian surfel representation to first sample rays which are used to render an RGB image. Second, we sample rays within each diffuse LiDAR pixel instantaneous field of view. For each sampled ray in each LiDAR pixel, we perform ray-surfel intersection, and then use alpha-weighted differentiable binning to estimate the histogram of the time-encoded depth returns for that ray. To then render a transient histogram for a diffuse LiDAR pixel, we sum together the histograms computed from each ray sampled within the LiDAR pixel, and convolve that with the laser pulse. We then compute a histogram loss comparing the ground truth transient measurement and our rendered measurement using KL divergence. And we compute a photometric loss on the rendered RGB image with L1 loss and SSIM loss. In doing so, we enable accurate estimation of RGB and novel view synthesis, as well as an accurate depth and normals estimation, which allows us to reconstruct a mesh of the original scene. It's important to note that unlike sparse LiDAR, direct point-wise depth supervision is infeasible from spatially blurred depth signals. Thus, a key contribution of our work is that we introduce a scene adaptive loss formulation to use diffuse LiDAR and RGB signals. Using our input RGB images, we compute both a patchwise texture weight based on image variance and a signal-to-noise ratio weight. Intuitively, we want to use the RGB signal in high texture and high SNR regions, and we wish to defer to the diffuse LiDAR signal in low texture, low SNR regions. Our scene adaptive loss weight helps capture this patchwise texture and SNR of a viewpoint, and can then be used in a sigmoid weighting to dynamically balance the photometric and LiDAR loss functions. We evaluate the proposed RGB and diffuse LiDAR reconstruction technique in 3 ways. First, we perform a recoverability analysis of diffuse LiDAR over sparse LiDAR. Second, we provide quantitative empirical evaluations in rendered low-texture, low-lighting scenes. Finally, we provide qualitative real-world experiments in challenging settings. We first analyzed the differences between sparse and diffuse LiDAR in a 2D scene recoverability analysis using an approximate linear model y equals ax, where A's structure depends on the LiDAR configurations, specifically the IFOV and the number of views. For a given number of views, we compute the rank of our A matrix for sparse and diffuse LiDAR. We find that our diffuse LiDAR in the limited input view regime has consistently greater rank and thereby recoverability. We operate within this view-limited regime for our work. Importantly, with sufficient number of views, we find that sparse LiDAR would eventually reach the diffuse LiDAR performance. We then evaluate our RGB and diffuse LiDAR method on a variety of low and no texture scenes. On full texture scenes, we find that we enable high-fidelity novel view synthesis. When we have textured objects on textureless planes, we find consistently that our method enables improved object plane disambiguation and peripheral region robustness, where sparse LiDAR might not have sufficient cues in distant regions to accurately reconstruct the plane. On textured plane scenes where the object is completely textureless, we find we estimate enhanced smooth geometry within the convex hull of the textureless object. And finally, on completely textureless inputs, we find that we have accurate 3D mesh recovery from sparse views, especially when RGB has no information and sparse LiDAR has poor coverage of the scene to accurately estimate geometry. Thus, we find that our RGB and diffuse LiDAR reconstruction approach can enable accurate color 3D mesh estimation across a wide variety of texture variations within a scene, particularly in low texture regions. This especially highlights the importance of our scene adaptive loss function, which can dynamically balance using RGB signal and diffuse LiDAR signal depending on which is more useful within the given setting. We additionally demonstrate in simulation that our RGB and diffuse LiDAR fusion technique can enable robust reconstruction in noisy, low-lighting scenes. Specifically, we find that our technique, as you continue to add noise to an image, can dynamically shift from using RGB cues to the diffuse LiDAR cues. Unlike our baseline techniques, which are unable to reconstruct the scene using RGB cues alone, or like our sparse LiDAR baseline, which doesn't have sufficient depth understanding to reconstruct effectively, particularly when RGB images contain no useful cues. Finally, we provide qualitative real-world evaluations of our diffuse LiDAR and RGB technique, and find that our method, like in simulation, can improve the object plane disambiguation and provide enhanced geometry and depth cues, particularly in low lighting, low albedo, and low texture scenes. For more information, please refer to our paper, and thank you.